Hello, hi. So last time we went through the definition of a vector space and did one example at great length about a case, namely a line through the origin, the line y equals 2x through the origin, that showed that it was a vector space. There are many different kinds of vector spaces, and today we're going to see a number of other examples and do some checks. So, for example, the 2x2 matrices are a vector space. The 3 tall vectors are a vector space. Many different kinds of vector spaces, and what we're trying to do today is to get used to those different kinds by seeing a lot of examples. Okay, so that leads me to the check-in that I want to do. Vector spaces are about linear combinations. Vector spaces are a place where linear combinations take place. So I want to, of course, do a check-in that connects to that. So the check-in is I want to look at the example from last time, the line y equals 2x, and remember what it means, conceptually, what it means to say it's a vector space. And then I'm going to contrast that with something that isn't a vector space. So question 1 says, consider the line y equals 2x. And so I have here the line y equals 2x. I rewrote it as 2x minus y equals 0 just because it fits with the second example that I want to do. So 2x minus y equals 0. And I'm going to do just to pick two vectors at random and make a linear combination and check that indeed the linear combination does give me a vector from the space. So I'm looking here for question 1 at for question 1 I'm looking at the line y equals 2x. So it's the set of xy where 2x minus y is 0. And I'm just going to pick two vectors at random from that space. Really, it doesn't matter what I do. So how about if I take v1 equals 1, 2, and v2 equals, and just really minus 3, and I want y to be twice that, so minus 6. Darn it, having a little trouble with my handwriting. And I'm just going to take a combination of the two, and any combination, it doesn't matter, but just to give an example, kind of a random pair, how about 5 times v1 plus 6 times v2? So let's see, what's 5 times v1 is 510, and what's 6 times v2 is minus 18 minus 36. And when you add them together, what do you get here? You get 5 take away 18 is minus 13, and 10 take away 36 is minus 26. And indeed, we started off with two vectors that had the property that the second component is twice the first. We took kind of a random combination of those two, and we ended with a vector that has the property that the second component is twice the first. So we're illustrating closure under linear combinations. If you start with two members of the space and take any combination at all, you end with a member of the space. So now the one way to understand something, to help understand something, is try to see examples where it doesn't work. So make a contrast. So I'm looking at the set of xy where 2x minus y is no longer going to be 0, but instead is going to be 1. And I'll pick two vectors again at random just to pick here. v3 is not supposed to be anything especially special. So if I take the x component to be 2, then that'll be 4 take away. I need a 3 there in order to get 1. And if I take v4 to be, 5, 2 times 5 is 10, so I need that to be a 9 in order to get 1. So I have two members of the space. And again, I'm going to take a random linear combination, just, whatever occurs to a person, and at the end, I will see that I do not get that twice the first component take away the second component is 1. So just illustrating that it's not closed by giving a specific example of it not being closed. So I don't know, how about 5 times v3, and then minus 2 times v4? I don't have anything in mind. I just made up some numbers. So 5 times v3 is what, 10, 15? And 2 times v4 is 10, 18. So when you do the subtraction, you get 0 minus 3. And it's obviously not the case that twice the first take away the second gives you 1. Twice the first take away the second does not give you 1. So this is an example where you take a linear combination, you end up with a vector in the same category as you started. Here's the case where you take a linear combination, you end up with a vector not in the same category as you started. This is closed under linear combinations. This is not closed under linear combinations. Vector spaces are characterized by the most important property, the conceptual idea of a vector spaces. You can take linear combinations and you can go nuts. You can take any linear combination you like and you'll still end up with a vector in the space. However, if you have a non-vector space, if you take a linear combination, you can end up outside the space. Okay. Okay, so that's the idea of a vector space. That's the concept behind a vector space. So let's see. Let's see here. So I want to talk today about some more examples of vector spaces and try to get across again some more of the concepts that illustrate here what it's about. So the main concept, there's a lot of detail here, but the main concept in this detail is line 1 and line 6. A vector space is a place where linear combinations take place, and these other conditions, the conditions that are not 1 and 6, it really serve to define what I mean by linear combination. You can multiply by a scalar. When you multiply by a scalar, for example, the multiplication distributes over addition. Or vector, or the addition of two things is the same either way, it's commutative. It's condition 1 and condition 6 that will most often concern us. That's what I tried to illustrate with the check-in. Last time we went through all 10 conditions at some length, trying to be careful and to say what each of them meant. This time we're going to go through a number of examples, so spend less time on each individual example, but try to illustrate that there are many different kinds of vector spaces. You might say, I have a vector space. Well, I have a different vector space, sort of thing. So there are many different kinds of vector spaces, and we're going to see a number today. Okay, so this is the one that we saw last time and saw it at great length. 4, 5, 6, 7, or checked all of the 10 conditions. And now I want to look at a new, instead of a line through the origin in R2, I want to look at a new collection of vectors, and this is going to be a plane through the origin in R3. The plane 2x plus y plus 3z equals 0 through the origin in R3. I have it drawn there in yellow. And I drew some vectors from the plane onto it. I had the computer draw that because I'm not a very good drawer. All right, that's a vector space under regular vector addition and regular vector scalar multiplication. Those are the operations that a person would think to do. That's what it means by natural operations. I'm not going to check every one of the conditions. I'm only going to look at condition 1 and condition 6 because I've tried to highlight those will turn out to be the conditions that most concern us. And again, I'm trying to make sure that a person can do the homework. That's absolutely right. You have to be able to work through the I's and J's, but also feels that they understand the concept here. Condition 1 is that if it's closure under addition, is that if you add two vectors in this space, add two vectors in P, the sum is you get a vector in P. Translating that into the geometry here, it says that two vectors in the plane add to make a vector in the plane. I'm going to confirm that algebraically, but before I do the algebra, here's the geometry. There's a red vector in the plane, there's a red vector in the plane. Both of those sit, not just their tip in the plane, but their entire body sits in the plane. Remember, this is a plane through the origin. So their entire body sits in the plane. When you add them, you are doing a parallelogram, and the entire parallelogram sits in the plane, so that the sum of these two vectors reaches to the far corner of the parallelogram. That one also sits in the plane. So the sum of the two vectors is also a member of capital P. Briefly, if you take two vectors in a plane through the origin and you add them, you get a vector in the plane through the origin because everybody's entire body sits in the plane. All right, so that's the concept, and the algebra, the thing that a person would think to do with I's and J's, is that if you take two vectors from the plane, P1 and P2, when you say they're from the plane, exactly what you mean is that if you take 2 times the first component plus the second component plus 3 times the third component, then you get 0. And over here, if you take 2 times the first component plus the second component plus 3 times the third component, then you get 0. So both of these vectors are numbers, and they have this property, and they have this property. Of course, when you add vectors, of course, they add component-wise. Of course they do. That's what we meant by natural operations. And then all I have to do is check that this vector, this is a 3 tall vector. Its first component is x1 plus x2. Its second component is y1 plus y2. Its third component is z1 plus z2. I have to check that those 3 components have the relationship that I want, the relationship from the previous page. This relationship right here is 2 times the first component of the sum plus the second component of the sum plus 3 times the third component of the sum. When you do that all together, do you get 0? So I check it. Here we go. 2 times the first component plus the second component plus 3 times the third component. Do you get 0? And of course you do. It would be embarrassing if I set the whole thing up and it didn't come out to be 0. You just do a little algebra, multiply the 2 through this kind of stuff, and it comes out to be 0. So to verify condition 1, I have to suppose I have 2 members of the space, a capital P, that satisfy the condition. That's what members of the space means. I then write down what is their sum, and I have to verify that their sum satisfies the condition. When you're doing the homework, you're saying to yourself, what does it mean to satisfy the condition? It means 2 times the first plus the second plus 3 times the third adds to make 0. So you start off the left-hand side of the equation, 2 times the first plus the second plus 3 times the third, and after some amount of head scratching here, it's not very much head scratching, you get 0 on the other side. All right, so of course, we're also going to verify the same thing for scalar multiplication. So I start off with a vector that is in the space. In this particular case, being in the space means 2 times its first plus its second plus 3 times its third makes 0. And I multiply it by a scalar. You can't multiply it by 7 and check just 7. That's not enough. You have to check for an arbitrary r. And likewise, too, the formal proof requires that you check for an arbitrary x, an arbitrary y, and an arbitrary z. This is not like the check-in where you check one and you figure they're okay. This is instead a formal proof, so I have to check it with letters. But nonetheless, it's not hard to see that r times p is this, and that p satisfies this. And what I have to do to finish is I have to verify that r times p is a member of the space. So I have to check that 2 times its first component plus its second component plus 3 times its third component makes 0. And so you write down there 2 times the first plus the second plus 3 times the third, and then you do not very much algebra, and you end up with 0, and they're done. Okay. The next thing I want to check is a vector space. You could think about checking the 2 tall vectors. You could think about checking the 3 tall vectors. You could think about checking the 4 tall vectors. All those, that's all true. I'm going to check all of them at once by checking the n tall vectors. This is a good illustration of my first example, really the first couple of examples. See the line through the origin and the plane through the origin. And I did those as first examples because they're not too easy. Sometimes examples can be too easy, and it's really not clear to a person what it is that's happening in that check. When you look at the n tall vectors, they're in some ways they're too easy. If I say the sum of 2 vectors, if the sum of 2 n tall vectors is an n tall vector, I don't know, it's very hard to understand what that means. But if I say the sum of 2, from the previous example, the sum of 2 members of the plane is a member of the plane, that's a little more meat to sink your teeth into here. But here, when I say the sum of 2 n tall vectors is an n tall vector, there's no restriction, and so there's nothing to check. That makes this in some ways a harder example than the first 2, or maybe not as good as a first example as the first 2, but it's still true. The sum of 2 n tall vectors without restriction is indeed an n tall vector without restriction. And likewise, the scalar multiple of an n tall vector without restriction is an n tall vector without restriction. So the collection of n tall vectors, the collection, for example, of 3 tall vectors is a vector space. The collection of 4 tall vectors is a vector space. The collection of 5 tall vectors is a vector space. I am not saying that the collection of 3 tall vectors union with the collection of 4 tall vectors. That's not right, because you can't add a 3 tall and a 4 tall. I'm not saying that. I'm saying instead that if you fix n and just look at, say, the 8 tall vectors, then the collection of 8 tall vectors is a vector space. The 8 tall vector plus an 8 tall vector without restriction, when you add them, you do indeed get an 8 tall vector. Okay, this is another example that's a good example because it's because it's at least slightly surprising. So I'm going to, as I illustrated in the last couple of videos, I'm interested in taking the linear combinations of any kinds of things where linear combinations make sense. One place where linear combinations make sense is it makes sense to add vectors, 3 tall vectors. Another place where linear combinations make sense is it makes sense to take linear combinations of 2 by 2 matrices. Well, here's still another place where it makes sense to take linear combinations. It makes sense to take linear combinations of quadratic polynomials. If you have 3 plus 2x plus 1x squared and 10 plus 0x plus 5x squared, it makes perfectly good sense and perfectly algebraically sensible to take 5 times the first and subtract 7 times the second and figure out what you get. And of course, we have to check that what you get is indeed a quadratic. So we know how to add quadratics. If you take a first quadratic and a second quadratic, you add them component-wise. That's exactly right. The constants, the coefficients of x, the coefficients of x squared. And we know perfectly well what it means to scalar multiply a quadratic polynomial. If you have a quadratic polynomial like 3 plus 2x plus 1x squared, you could perfectly sensibly multiply it by minus 106. That is to say, you simply multiply component-wise, r times a naught, r times a1, r times a2. And the intuition always in these cases, always, you want to be able to do the sort of pushing letters around to get the homework. That's very important, that a person is keen on getting the answers, doing well in the quizzes, but just simply learning what it is that they're required to do. But you don't want to lose sight of the concepts. The concept here is that vector spaces are about taking linear combinations. It makes perfectly good sense to take a linear combination of these vectors. Makes perfectly good sense to take a linear combination of 1 plus 2x plus 3x squared. You call that a vector in this context because it's a member of a vector space. It makes perfectly good sense to take 4 times that, a minus 1/5 times 10 plus 5x squared. That has, you can think of it as having 0 times x written in the middle. And what you get is a quadratic polynomial. So a linear combination of quadratic polynomials is a quadratic polynomial. That's closure under linear combinations. That's the key to being a vector space. So so a person has to be able to check with the letters. That's absolutely right. But don't want to lose track of the concept. The concept is that you can take linear combinations of these guys and you get one of these guys. Now, I'm not going to give a full verification, but I will give the check for conditions 1 and 6 because those are the 2 key conditions. So for number 1, I start off with a first quadratic polynomial, and there's a second quadratic polynomial. I use the a's and b's. First quadratic polynomial, second quadratic polynomial. I don't know why this one has parentheses around it. And then I add them, and I'm simply going to verify that the sum is a quadratic polynomial. So I add them. Of course, you know how to add them. I'm verifying that it's a quadratic polynomial because it's a constant term plus some linear term plus some quadratic term, and there's nothing else. This is not like when you square a quadratic, you get 4th powers. No such thing happens here. This is when you take a sum of 2 quadratic polynomials, you get a quadratic polynomial. That's all. Likewise, for condition 6, if you give me a quadratic polynomial and you multiply it by some number, 0 or 2 or 107, it's still a quadratic polynomial, or the result is a quadratic polynomial. That's all this 6 says. One thing that happens sometimes with these, when you consider a new system and you start looking at the rules seems a little strange when you first see them, and you go through a number of examples, and then at some point you start saying, oh, is that all it says? That's what's happening here. That's all it says. 3 by 3 matrices. I'd rather do one example too many than one too few. So here we are, 3 by 3 matrices. A person can add a pair of 3 by 3 matrices, and a person can multiply a 3 by 3 matrix by a number like 5 or 10 or minus 6. And that's a vector space under the usual matrix addition and scalar multiplication. The check is perfectly simple, but I don't want to lose track. This is not the answer, but this is to get across the concept that you can take linear combinations of 3 by 3 matrices and you get a 3 by 3 matrix. So here I have them take 1 times the first minus 3 times the second, and you do the arithmetic. I hope I did the arithmetic. Do the arithmetic, and you get a 3 by 3 matrix. So a linear combination of 3 by 3 matrices is a 3 by 3 matrix. Of course, I might put some restriction on 3 by 3 matrices and have to check that, just like I check the case for planes through the origin or lines through the origin. I could, for example, write down, what about the 3 by 3 matrices that have the property that the upper left entry plus the lower right entry adds to 0? That's not this example, but you could look at cases like that and there would be more to check. But conceptually, at first glance, when you're first approaching vector spaces, what the heck is a vector space? Vector space is about, you can take linear combinations and not have to be concerned that what's on the right-hand side of the equation is not a member of your space. That can't happen. Vector space is where whatever you do on the left, you'll be good on the right. Okay. A couple of small results that follow from the definition. First of all, the empty set isn't a vector space, because the definition requires that the space contain the additive identity, the 0 vector. So it's got to contain at least one thing. So there you go. You can have a vector space that has only one element. That can happen, and I listed as an example the vector space that contains only the 2 tall 0 vector, and that the plus and times operations are pretty dopey there, but it's still perfectly possible and satisfies all the rules. You call that the trivial space for the obvious reason, and we'll have occasion sometimes to mention the trivial space for much the same way that you have occasion in high school algebra to mention the number 0. It just comes up sometimes. Next up is a small lemma. When you look at the 10 conditions for vector space, a person can say, well, where'd those 10 rules come from? Why, for example, include the rule that 1 times v equals v, but not the rule that 0 times v equals 0? And the answer is, it so happens that some of the rules imply other rules. So, for example, we don't need 0 times v equals 0 because from the 10 rules we have, we can derive it. Oh, why include this one? Why leave that one out? Well, that's a question when you're constructing the definition. You try to make it work so that it's convenient as possible, and the verifications of the extra conditions are not too hard, this kind of stuff. We're not going to go into the details of that, but the point is that some of these rules follow from the rules we already have. So if you're saying, why did we leave off? Well, we left it off because we don't need to add it. And the proof of most of these is kind of a fiddling around algebra stuff. So to show that 0 times v, if you use the scalar 0, you get the 0 vector, I took v, I rewrote that as 1 times v, which I then wrote as 1 plus 0 times v, and then I distributed 1 times v and 0 times v, and then I basically have a v and a 0 v, and I subtracted off. Anyway, a little bit of algebra fooling around. Don't get too concerned about this. A little bit of algebra fooling around gets you the rule here. Sometimes I've had folks raise their hand and say, are all the things we do in the rest of the semester going to be like rewriting things in the... No. Okay, this just so happens that the technical manipulation to say that you don't need this rule among the 10 is a little bit maybe overly slick. And item 2 and item 3 are along the same line. They're not especially tricky. Just as an example for item 3, r times the 0 vector is a 0 vector. If you don't think of the 0 vector as a 3 tall vector, if you think it could be a bunch of things, it might be the 0 vector might be the 2 by 2 matrix that is all zeros. The 0 vector might be the quadratic polynomial that has all 0 coefficients, 0 plus 0x plus 0x squared. Then 3 becomes a little bit less obviously true. But it's easy to verify r times 0 is r times 0 times 0, r times 0. Anyway, again, the rest of the semester we will not be doing this kind of algebraically pulling things out of the air. Nothing about these are illegal. They just sometimes give a person an uneasy feeling that they're going to start being asked to do tricky things. No, we're being asked to follow the concepts here. That's what we're keen on. Okay, next time we're going to talk some more about vector spaces by virtue of talking about something called subspaces, but I want to emphasize that we will still continue to practice the idea of vector spaces, and that a person is being exposed to something that's brand new, and you're not just sort of expected to instantly snap it up and it's all perfectly obvious. That the best thing to do here is to see lots of examples, and that's exactly what we're going to see. Okay, all right, bye-bye.